Hi. The Sieve of Eratosthenes is one of the most important algorithms that is used for finding prime numbers, and it's an algorithm that was uh, discovered, or it's attributed to this philosopher and mathematician by the name Eratosthenes of Cyrene. That's around the years 276 BC to around 194, 185 BC. And the algorithm is used to find all prime numbers less than or equal to some integer n. And we know that this n is greater than 2. Now, it is called a sieve because it acts like a sieve. It receives or it can accept lots of numbers, and then we call those numbers composite numbers, and then it will only allow things to go through, and those numbers that are going through are the prime numbers. When we look at what Wikipedia talks about, it says that in mathematics, the sieve of this guy is an ancient algorithm for finding all prime numbers up to any given limit. And then it goes on saying that it does so by iteratively marking as composite the multiples of each prime, starting with the first prime number 2. The multiples of a given prime are generated as a sequence of numbers starting from that prime with constant difference between them that is equal to that prime. So this is the sieve's key distinction from using trial division, blah blah. So it is known to have been used in ancient Greek, and it works in a very interesting way. Now, oh, what happens? This algorithms has got four main steps or stages or phases, and then once the phases are iterated, or once somebody goes through them, you'll definitely get your prime numbers. So here we say that given a list of many numbers, it will only give out, something is missing here, the prime numbers, or it will only allow the prime numbers to go through. So the algorithm states like this: start with the list. So from 2 to n, all the numbers, composite numbers. So starting from 2, and then it says declare p to be prime. So this cross off, delete all multiples of p except p from the list. So for example, if we start with 2, 2 is going to be our prime, and then we're going to delete all multiples of 2 and then leave 2, and then it goes on, then find the next number in the list. Now in this case we can go to 3, and then you delete all multiples of 3, and then after doing that you again go to the next prime one. So, and then it keeps on going like that, iterating until it stops. Now the third stage or phase or step is to find the next number in the list after p that is not yet crossed off, and set p to that number, and then repeat from step 2 down that. So the algorithm will only stop when p is greater than the square root of n. Now that is very, very important. Now, for example, we want to set that our n is is 100. So our algorithm will stop when this p is greater than 10, because the square root of 100 is 10. So when it hits 10 or something, or some value above 10, then the algorithm will stop. So what usually happens is this: the first thing to do is to list all the numbers. Now in our case, n is 100, so we built a table here having these 100 numbers or integers. Now this is what happens. We all know that one is not considered, and we begin at 2. Now the very first step is here: start with the list at 2. So 2 is our prime number. So what happens? The next step is declare p to be the prime. Yes, we've done that. And delete all multiples of p. So we know that if 2 is a prime, all multiples of 2 are right here: 2, 4, 6, 8, 10, etc. But then since we have it as a table, all this will go followed by this, followed by this, followed by this, and that is why we have this column all taken away. So we are already eliminating all the multiples of 2. Now the step 3 states this: find the next number in the list. Now after we've done that, we are through with the deleting all the multiples of 2. The next number in the list is now, after 2 is 3. Now in this case it's 3 here. So what is going to happen now? Put the next number in the list after p that is not yet crossed off, and set p to that number, and repeat from step 2. So we set it to p, and then we declare it to be a prime, and then delete all multiples of that p. So if it's 3, we set it to be prime and delete all the multiples of 3. Now what happens? All the multiples of 3 are deleted, and that is, for example, 9. Another 3 times 3 is 9, 15, 21, etc. So what happens? We get this, and then we again do this very same thing. You find the next multiple after 3. It's the next number after 3 is 5. So 5 will also set it as a prime. After setting it as a prime, we are going to delete all its multiples. So we know that all numbers ending with 5 and 0 are, of course, multiples of 5. We'll delete all the elements in this row and all the elements in this row, but luckily they are already deleted. So what happens? So we have here 5. So after doing that, the next number that's not deleted is 7. 7 is set to be prime. After it's set to be prime, all its multiples are also deleted. Once they're deleted, we'll have this. Now once we have this, the next prime is 11. 11 is greater than 10, so our algorithm stops. So what is left here? What is left here is actually the prime numbers, and these prime numbers are right here. Now this is the theorem. It works efficiently. You can see it being uh, automated. Here, for example, we can just it states like this: that repeat the action, remove all proper multiples of the next remaining prime in the table. Okay, it says start with the number 2. So the multiples will be removed by clicking the prime. When all proper multiples of all numbers in the first row are removed, the table will contain only the multiples, only the primes except 1. So we're going to start with 2. So I'm going to choose a color. For example, here I'll choose this n is equal to 100, just what we've just done now. I choose here, yes. So it's selecting all the multiples of 2, and we can see them in all those columns. Now that is very clear. Now all multiples of 2 less than or equal to 100 are colored red. So after that is that, we are like striking them off. The next prime is 3. Let me choose another color, which is blue. I come to 3 here and I click it like that. So all the multiples of 3 are again crossed off. Now all multiples of 3 less than or equal to 100 are colored blue. So this is the second iteration. Now I choose another color, and then we see this one has already been removed. So the next prime is 5. So I will select 5 right here, and now 5 will remove all, yes, that are left here, all multiples of 5 that are less than or equal to 100, and of course values that are having a 0 at the end, the multiples of 5, they're also going to be removed. The next, this one is already removed, is already removed. 6 is already removed. So what is left here? I choose another color. Let me choose this pink, and then I put it right here on 7. So all the multiples of 7 less than or equal to 100 removed. And now what happens? Now the algorithm stops, and we have the list of all the prime numbers right here. And that is how this algorithm works.